What's up, guys? Got a bit of a different video today. We're going to be doing the unit circle and some trig identities. Now, this isn't going to be like my differentiation integration video where I've spent like 5 minutes on the entire slideshow. This is actually like I put a lot of effort into this unlike the other video, and I'm actually going to explain it decently this time. So let's get started. So if you don't know what the unit circle is, it's just a circle like this on the graph with as you see, this is 1 and it has a radius of 1. So the radius is 1 unit. Whatever this radius is across the circle, it will always be 1. And we're going to label this as 1 unit. So now we're going to label this angle theta. Right now it's probably around 45, but it doesn't matter. It can range because that's what it's all about, the unit circle, like predicting what happens at any degree. So we're going to draw both these lines here on the circle, the red line and the black line. Now, and we're going to remind of like simple SOHCAHTOA. So this bottom line here, it's going to be, we know that the adjacent equals cos theta times hypotenuse, but we know that the hypotenuse is 1. So adjacent just equals cos theta, which means that this is just cos theta, this line right here. It's a bit weird that a length is something to do with cos, but it's just cos, but just bear with me. This length is also going to be just sine theta because it's opposite over hypotenuse, and the hypotenuse is 1, so the opposite is just going to equal sine. Now we've drawn this out, we're going to go back to this triangle here. As we've drawn it out, we've moved it off the graph so we can prove the identities here. So we know Pythagoras theorem, of course, and you can see here we have a right triangle. I haven't labelled the right angle, but this is a right triangle because it is perpendicular, these two lines. And we know that because it's Pythagoras, we know that sine squared theta plus cosine squared theta equals 1 because of this triangle here. We also know that tan theta equals opposite over adjacent. We know theta's right here, so opposite over adjacent is just sine theta over cos theta, which means that tan theta always equals sine theta over cos theta. Alright, we're going to go back to the unit circle now, and we're going to get this side here. This is a tangent, as you can see, and we're going to label it x. Now, we're going to label these two, this is a right angle here. We're going to label this right angle, and we're going to label this right angle. Now, we label this theta, and we know, because of this, both triangles will be similar. Both the left triangle and the right triangle will be similar, because the sine theta line bisects the right angle like this. And we know that these will both be 45. Then, both the top angles are equal. We know that there are two right angles here, and we both know that both these angles are theta, therefore they're similar. So what we can do with this is find this line here. If we draw the triangles out again, like this, and we're going to rotate the right one, we can find the scale factor. So we know the scale factor is x over 1, because we know how scale factors work. But the scale factor is also, because we have two other lengths, the scale factor is also sine theta over cosine squared theta, cosine theta. So we know that x over 1 equals sine theta over cosine theta, which means that x equals sine theta over cosine theta, which means that x equals tan theta from what we proved earlier. So now, if we go back to our unit circle, we know that this is tan theta, this half tangent here. Next, we're going to find this length here, this big length down here, and we're going to label this x. So now we're going to redraw the triangles again up here, and we're going to shift this triangle around a bit just so we can do it better. And we know if we label this L, this smaller length here, we can know that x equals cosine theta plus L. Now, you can prove this with similarity, but I find it more logical to prove it using trig identities. So we're going to use Pythagoras again to know that L equals root tan squared theta minus sine squared of theta. So as you can see here, this is our right triangle we have. So now we're going to have to solve this, or we're going to have to simplify it down. So we can firstly square it, and we can convert tan squared into sine squared over cos squared. Then we're going to convert sine squared into sine squared cos squared over cos squared, because we need to put the fractions into one fraction. Next, we're going to put them both into one fraction, and we're going to factorize sine out. Then, we know that 1 minus cosine squared theta equals sine theta from the Pythagorean identity earlier. And so we can know that sine to the 4 theta equal over cos squared theta equals L squared. Next, we're going to root it to get L equals sine squared theta over cos theta. And we're going to use the Pythagorean identity again to get this fraction here. And now we're going to separate the fractions, cancel the cos's out, and we have an expression for L that we can't really simplify down anymore. Because now we know that x equals cos theta plus L, we can just substitute L here. So we x equals 1 over cos theta minus cos theta plus cos theta. And if you know how to simplify, which you should, then you get x equals 1 over cos theta, which we can write as a secant of theta. So that was a bit of a long proof, but at least we know now that x is going to be secant. Alright, we're going to go back to the unit circle now, again, and we're going to label this as a secant. Now, we're going to go to the other side of the circle, and we're going to look at this length here, or this, I've labelled x again, and we're going to, firstly we're going to move these lengths up because it will be useful for later, so we know that this is also cosine theta, because they move the same direction on the x-axis. And next we also know that if we move this across, this is also sine theta. Then next we're going to do the same thing we did earlier, and we're going to move it into a triangle, 2 triangles. Right, so we're going to apply the same similarity rule that we did for tan on this. So we know that x over 1 this time equals cosine over sine. So this here, cosine over sine. Not this cosine over here, this, because these are the same lengths. You can't use different lengths for triangle similarity. So we know that x equals cosine theta over sine theta, which means that x equals the cotangent of theta, because we know that if sine theta over cos theta equals tan, then if we just find the reciprocal, that means that 1 over tan equals cotan. Right, we're going to go back to the unit circle again, and we have one more length to find, which is this one here, this big length here. We found secant over here, so you know this it's going to be related to secant. You might be already know how to guess which one this is. And we're going to label it x, and we're going to do the exact same thing we did earlier. We're going to put this out, we're just going to take everything away, and then we're going to re-rotate it, and you might recognise this form from earlier where we have the 2 triangles and then the L. So we're going to go through the same trig proof again. I won't explain it as much, because if you don't understand it, you just go back to the other proof, because it's basically the exact same thing, but the cos and the sines are switched around. So we know that L equals this right here, because of Pythagoras, this left triangle here. And then we convert cot into cos over sine. We put the cos on top of the fraction, and then we factorize cos out. We use the Pythagorean identity again to get cos to the 4, square root, and then we use the identity again to get 1 minus sine squared, and then we separate the fractions. Then we substitute into x like we did earlier, because we know x is sine theta plus L because of this sine theta right here. And we can simplify to x equals 1 over sine theta, which, as you might have guessed, is the cosecant of theta. I mean, it says x there, but that's just a typo. X equals cosecant of theta. Alright, now we're going to go back to the unit circle, and we're basically done here. It's got a bit crowded, as you can kind of see, but we've kind of proven at all 6 of the main trig functions here. Now we're going to just kind of look at what we can actually do with this. There's many things you can do with this, but I'm just going to outline a few. So firstly, we know that the cotangent, the cosecant, and the just cos itself is just the same as tan, secant, and sine, just with the complementary angle, which is this one over here, or just 90 minus theta. That's why they have co in their name. It just stands for the complementary sine, the complementary tan, and the complementary secant. We also know that because of this triangle over here, the one that we made earlier, we know that 1 plus cot squared theta equals cosecant squared of theta because of this triangle up here. That's an identity we need to know. This is another identity with the biggest triangle here, so the cosecant, the secant, and then the tan and the cotangent. This is an extremely long way to prove that this identity here, it eventually simplifies down, but it's a bit impractical. Also, if we were to change theta, if we were to move the radius up to where theta goes closer to 90, you would notice that tan would become completely horizontal, which means it would have no solutions, and that's why tan 90 is undefined, because it won't be able to cross the x-axis, and it won't form a triangle with secant at the bottom. Yeah. This is also the same with cot, because it will also become horizontal if it goes to 90. Also, this also proves that sine cannot go over 1 because the radius is 1, so it can't extend out of the circle because that's not how it works. And I think that'll be it, guys. Thanks for watching, and hope you understand the unit circle a bit more, or anything from the unit circle a bit more. If you don't understand a few of the things, hopefully you can understand some of the earlier stuff in the video. But I will see you later for the next important part video, where we'll probably go through another paper. Goodbye.